Welcome to our video on synthesizing agentic data for web agents with progressive difficulty enhancement mechanisms. This research was a collaborative effort by Salesforce AI Research and the University of Wisconsin-Madison. Today's web agents often fail on long-horizon reasoning, tasks that require multiple search, browse, and analysis steps. Most large language models aren't optimized for multi-turn exploration. Existing datasets are usually too simple and lack control over how task difficulty increases. So our motivation is to create a synthetic data pipeline that produces progressively harder question-answer pairs, letting agents practice and improve step by step. Our approach is called ProgSearch, a two-pronged data generation pipeline. The first branch is a top-down synthesis, which starts from a seed concept and builds a tree of facts to craft increasingly complex multi-hop questions. The second is a bottom-up synthesis, which begins with a rare anchor entity, something the model rarely sees, and builds questions around it. A baseline web agent monitors and regulates the difficulty, ensuring each QA pair is factual, unique, and sufficiently challenging. In the top-down route, we begin from a seed entity, such as Stanford University. A researcher agent expands outward, linking related entities like Palo Alto to Bay Area to California, forming a tree of facts. A questioner agent uses these facts to craft multi-hop questions, and a solver agent attempts them. Difficulty rises until the solver fails, indicating the question has reached the agent's capability frontier. This diagram visualizes that process. The researcher builds factual links, the questioner generates a question, and the solver tries to answer. When the solver succeeds, we expand the fact tree further to make a harder question. When it fails, we record that final QA pair as a verified, difficult example. The algorithm for generating tree of facts linking related entities. Goal: build a growing network of connected facts starting from one topic or entity. How it works: begin with one seed entity, for example, Stanford University. A researcher agent searches the web to find one factual link, such as Stanford is in Palo Alto. It then keeps expanding outward, finding new related facts like Palo Alto is in the Bay Area is in California, and so on. Each new step must introduce fresh information, not something already mentioned before. This continues until no new relevant facts appear, or a preset depth limit is reached. Result: a structured tree of facts that chains together related ideas, forming the base for multi-step reasoning questions. Algorithm for generating top-down multi-hop QA pair. Goal: turn the tree of facts into questions that get gradually harder until the model can no longer answer them. How it works: collect the first few facts from the tree and give them to a question creator agent to make an initial question and answer. A validator agent checks that the question is clear, realistic, and needs reasoning. A solver agent then tries to answer. If it succeeds, the question was too easy. To make it harder, add another layer of facts from the tree and ask the question creator to rewrite a tougher version. Repeat this cycle: generate, test, and expand until the solver finally fails. Result: the last question it fails on is saved as a verified challenging example for training. For the bottom-up approach, we select a rare, low-contamination entity as the answer. Questions are generated indirectly referencing this entity, iteratively obfuscated, and constraints are added. The process stops when the solver fails and the QA pair is verified. This diagram details the bottom-up data synthesis process. It begins with anchor entity creation, moves to initial question generation, difficulty enhancement, and concludes with a robust verification stage. The algorithm for the bottom-up approach outlines how QA pairs are generated. Goal: create difficult questions that point to one rare or uncommon entity as the answer. How it works: pick a rare entity, something with little web presence, to serve as the fixed answer. The question creator agent makes a simple question about it. The solver agent tries to answer. If it gets it right, the question is rewritten to hide clues or add extra reasoning steps. This hardening loop repeats, each time making the question more indirect and complex. When the solver finally gives the wrong answer, that version is accepted. A final check confirms that the question is factual, clear, and has only one correct answer. Result: a set of well-grounded, high-difficulty question-answer pairs focused on rarely seen topics. Our filtering and validation process ensures high-quality data. We apply consolidated filtering based on question readability and reasoning depth, perform factual verification using URL-backed facts, and filter out alternative answers. This results in precise, factual, single-answer questions. Starting from around 40K questions in 2-wiki multi-hop QA, we generated 12K synthetic QA pairs, and after filtering and distillation, kept about 6K high-quality samples. Each training trajectory averages 20 tool calls, some reaching 94. Though smaller, ProgSearch is far richer and more complex than previous datasets like TaskCraft or Asearcher. In our experimental setup, we used Qwen3-8B and Qwen2.5-7B-Instruct models. Training involved supervised fine-tuning with rejection sampling. We benchmarked against Frames, GAIA, HLE, and BrowseComp, maintaining strict contamination control. Our results demonstrate that models fine-tuned with ProgSearch consistently outperform those trained with other methods across all 4 benchmarks, indicating significant improvements in performance. Analyzing tool use, ProgSearch data shows an average of 20 tool calls per trajectory. Agents trained with our data exhibit a lower tool error rate of 0.5%, indicating improved reasoning efficiency and smarter tool planning. Further tool use analysis shows that ProgSearch significantly reduces tool error rates and improves benchmark accuracy on both Frames and GAIA datasets. In summary, quality beats quantity. Progressively hard examples produce better reasoners. Difficulty is calibrated to the model's ability using a baseline agent. Agents trained on ProgSearch generalize better and use tools more effectively. Overall, ProgSearch proves that structured synthetic data can significantly enhance web agent performance. Thank you for watching this video. We hope you found the information insightful.